Hello everybody. My name is Dan Hatfield. I'm a PhD student at DTU Wind, and I'm part of a EU-funded project that focuses on floating wind turbines. And as part of this project, I get to work with Gilles in climate scale for the past month and then for the next few months. And here I'm focusing on atmospheric stability in the context of climate change. So the whole idea of atmospheric stability is the capability of movement within the atmosphere. So if where do I want to say? If a particle wants to move up, depends on how heat flux works, how the momentum flux is going all together. And basically this can be broken up into two different categories. So there's one, it's turbulent flow or unstable atmospheric conditions. So here we have a positive heat flux. So the air is warmer than the surface. So this means we get high turbulent conditions, lots of movement, a very deep atmospheric boundary layer. And so in terms of wind energy, right, if we're looking at this offshore wind wake and we're dealing with unstable conditions, we get these long, poofy wakes that are from a high wind deficit. And the other side of this is stable atmospheric stratification. So this is inhibiting motion within the atmosphere. So again, a negative heat flux, so colder air, warmer surface. And in this case, we get very laminar flow. So we have these nice streamlined wakes, but with long wake recovery times. So both have their negative impacts on offshore wind energy and offshore wakes. And so when we're looking in the climate context of climate change, right, we tend to look at the wind speeds, the temperatures, precipitation, where stability has a combination of the two and is a bit more impactful when we're dealing with wind energy. Atmospheric stability drives winds at hub heights and then therefore the total energy production. So if we're actually going to, what am I trying to say? If we're actually going to quantify stability, the main way is to ratio your destabilizing effects to your stabilizing effects. And the way I'm going to be focusing on is the Obokov length, which again is more directly related to wind energy. And I'm going to break it down into 5 different classification schemes. So our extreme cases, so very stable, very unstable, and then our neutral case, where we have a balance between these destabilizing effects. And so when we look at the marine boundary layer, especially in the North Sea, typically we're dealing with unstable atmospheric stratification. So this is turbulent, this is positive heat fluxes. So what I'm going to be taking is ERA5 data. I'm going to take 60 years of ERA5 data, calculate the Obokov length at every single 10-minute time step, and see the frequencies on a yearly time scale. I'm going to do this in 8 locations throughout the North Sea. So Fino 1, Doggers Bank, the high wind location, east coast of the UK, Dutch coast, Belgian coast, English Strait, and the Irish Sea. And then if I actually plot these on a yearly basis, for example, here we have our very stable cases all the way to our very unstable cases, we don't really see a huge change. If we actually plot this and show this in a yearly average basis, we see more of on the average of 1 to 2% increase in unstable cases, so more turbulent atmosphere, lower wind speeds, and a decrease in stable conditions. But because this is very temperature driven, it's very important. It's very dependent on the differences in temperatures. Looking at it on a yearly basis is not really representative of the whole process. And so when we actually look at this in terms of seasonal, this is where we start to notice some differences. So here for winter, for example, I have very unstable all the way to very stable or a very unstable. And I take these frequencies on a yearly basis, do a rolling average, and look at the rate of increase. And we see a shift towards neutral conditions. So this is around 8 to 9% increase and a decrease in very unstable conditions. So this is shifting away from lower wind speeds into a regime or into an atmosphere where we're getting higher wind speeds and more extreme speeds. On the other hand, when we're looking at summer, we see the opposite effect. We're moving away from stable atmospheric stratification towards more unstable stratification. And this is leading to lower wind speeds or lower overall wind speeds. And so you can do this for all of these 8 locations. So again, this is for the 8 locations, each of the classifications of stability and each of the seasons. And I could go through all this, but for sanity's sake, we're just going to take the case study of winter. And in all cases, in every single case throughout the North Sea, where we have different predominant wind directions, we have different proximities to land, we're seeing an increase in neutral conditions and a shift away from unstable conditions. So this is leading to higher overall wind speeds. For example, if I take the Weibel or the distribution of wind speeds in the 1960s, now Gilles did mention that when we're dealing with ERA5, there's a bit higher uncertainty associated with the 60s and before the 1979. But for sake, here we have our very stable and very unstable conditions, typically associated with lower wind speeds, and neutral conditions with higher wind speeds. And so then if we take the Weibel of the previous decade, so from the 2010s, we're shifting towards more higher wind speeds. So this is away from these very unstable, very stable cases towards more extreme winds, and so more neutral conditions. And to give an estimate, this Weibel compared to this Weibel shows an increase in power of 15%. And we can see this in all cases, right? The UK, where we're seeing the smallest increase in neutral conditions, still has a shift towards higher wind speeds in the winter. Same with high wind, same with Dogger's Bank, all these locations in different areas of the North Sea. Looking towards temperatures, here we see the temperature distribution from the 1960s, the decade, and the temperature distribution from 2010s. And basically, we're seeing a shift towards, so these are temperature difference of air temperature at 2 meters and the sea surface temperature. Here we're seeing a shift to more equal temperature differences, or a shift between -2 and 2 between the temperature, compared to the bulk or a larger difference in the 60s. And this can be attributed to the different rates of increases of our air temperature compared to our sea surface temperature. So in the North Sea, at least in this portion of the North Sea, this is around Pheno 3, we're seeing the air temperature increasing at a higher rate than our sea surface temperature. And this is leading to differences in the temperature difference, which is leading to differences in a heat flux, which is leading to overall more neutral conditions, and therefore more higher winds or higher wind conditions. And so this can be seen, and again, in all these different locations, in Dogger's Bank, in high wind, and even in the East Coast, where we're seeing a smallest increase of to neutral conditions, we still see a slight difference between the increase of our air temperature and our sea surface temperature. So I'm just going to leave this up as a summary of what we're seeing. And one thing I didn't really talk about were the summer months or the spring months, where as we're seeing stilling in the last location, or in Gilles' presentation, he showed this variable of the Irish Sea, where in the 80s and 70s, there was an increase in wind speed. Looking at the winter, we're actually seeing some increases in this, where in the summer and spring, we're seeing more of a shift towards unstable conditions, and therefore more or lower and lower wind speeds. But thank you.